Hello there, and welcome to this collection of notebooks and tutorials on advanced digital signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, and this notebook is about the Lloyd-Max Quantizer. So we are going to talk about the concept of the Lloyd-Max Quantizer, and then we'll end up with two examples. Let's get started. The idea behind the Lloyd-Max quantizer is to reduce the quantization error where signal samples appear most often. So we choose our quantization steps smaller where signal samples appear most often, and we make the quantization steps larger where there are only a few samples. So this is not quite the same as the mu law compending. There the small values get the smallest quantization steps, and here the most likely values get the smallest quantization step sizes. So this is a type of non-uniform quantizer which is adapted to the signal's PDF. So it minimizes the expectation of the quantization power. So it's the expectation of the squared signal or its second moment given the PDF of the signal to quantize. So if we call our quantization function q of x, so this is quantization followed by reverse quantization or dequantization, and we have the expectation of the quantization error power given by this expression here. So we have d is our quantization error power, e here is calculation the expectation, here we have our signal minus the quantization function, and here is our squared. So our goal is to minimize this expectation of the quantization error power. So we will start with the PDF of our signal, and the result should be our quantization intervals and our reconstruction values. Yeah? So now we have non-uniform intervals, so we need to give general names for reconstruction values and for the decision boundaries. So we'll call a y of k the reconstruction values at index k, and b k minus 1 or bk. So those are the decision boundaries. So the idea is to minimize this expectation, and as a result we will have quantization intervals and reconstruction values. So the y of k's and the b of k's. The encoder knows the decision boundaries, knows the b of k's, and decides in which interval, what we call delta before, the sample lies, and assigns the interval index k to it. Only the index k is transmitted to the decoder. The decoder takes this index and assigns the reconstructed value y of k to it as before. We call b of k the decision boundaries. So in the AD converter or encoder, each interval gets an index as before, like we did previously, and on the decoding side we have the y of k, the reconstruction values for each index from the encoding side. In the multidimensional case, they are also called a code word. So using these definitions, and we have the PDF of our signal, we can rewrite this equation by this here. So here we are including the probability distribution of our signal p of x, and here we are calculate the expectation of the power, the error power or the distortion. But this integral can be subdivided over the quantization intervals. So if we assume that we have m quantization intervals, so we can add the quantization error power of all the quantization intervals, and we go from here to here. So we are subdividing this integral over the quantization intervals, and we have this summation over all the quantization intervals. So what we would like to know is to have the minimum of this expression for the decision boundaries b of k and the reconstruction values y of k. So what we do is that we take the first derivative of the distortion d. So this is the expectation of the quantization error, so it's the quantization error power and we will take the first derivative of this equation, and then we will obtain the 0 point. Yeah? So we have d, and we'll have to do this for the b of k, the decision boundaries, and the y of k, the reconstruction values. Let's start with decision boundary b of k. So we want to find the minimum of this equation here for b of k and y of k. What we do, we take the derivative with respect of those variables. So we start of the decision boundaries b of k, so we take the derivative of this equation in respect to b of k, and we set it to 0 to obtain its 0 point. So what we can do is to solve the integral over two neighboring quantization intervals, because each decision interval b of k appears in two intervals, one where it is the upper boundary and one where it is the lower boundary. So we have here the lower boundary and we have here the upper boundary. So we're dividing the integral, solving it over two neighboring quantization intervals. And we come to the conclusion that we cannot get a closed form solution for a general probability function p of x. Yeah? So what we can do is that we can make the assumption that the p of x is approximately constant over our two neighboring quantization intervals. Yeah? So this is a very important assumption. This is how the algorithm is derived based on this assumption. So we are assuming that the probability p of x is approximately constant over two neighboring quantization intervals. Yeah? Therefore, when we don't have a closed form solution for a general probability function p of x, we will assume that it's approximately constant over the two neighboring quantization intervals. So we divided we're solving the integral over two neighboring quantization intervals, and we're assuming that the probability function is constant over two neighboring quantization intervals. Yeah? So then we can set that the p of x will be just a value of p, and then when we solve this equation here, we end up with this thing here. So we use this simplification. We assume that the probability function is constant over two neighboring quantization intervals, and we can solve this, and we have d of k divided by p is equal to this equation here. So what we'll do is to solve this using SimPy. So it's exactly this. So we just go from here to here using SimPy. So I'm importing from SimPy equation symbols, integral, derivative, simplify, solve. I'm defining the symbols x, y of k, y of k1, p of k here. Then I am defining here this integral, which is exactly the same as this integral here over two neighboring quantization levels. So we have from bk minus 1 to bk, which is this part here, bk minus 1 to bk, and then we also have the bk to bk plus 1. So when we solve, we have this, the tk is this here, which is just the expanded version of here. So we have this to the power of 3. If we expand here, we have the p here and this 3 here. So we have the p is here, so dk divided by p, and then we have this 3 here. So it's the same thing we just solved using SimPy from here to here. Now we have a closed form solution of this integral here that is given by this equation here, which is the same as what we've seen here. This is non-expanded form, and this is the expanded form. So what we need to do is take the derivative in respect to b of k, and the result is given by this equation here. So what we are doing now is we take this result here, and we are taking the derivative with respect to b of k, and we have this result here. So if we expand this, we will end up with this, which is just solving the derivative with respect to b of k using sim_pi. So now we have this derivative, and we can set this to 0. So we will have this equation here, we will set it to 0, and we will find the b of k. So this means that we put our decision boundaries right in the middle of two reconstruction values. Yeah? This is, we assume that the signal PDF is roughly constant over two quantization intervals. Yeah? And this approach is also called the nearest neighbor, yeah? Because any signal value or data point is always quantized to the nearest reconstruction value. Yeah? This is a very important result of this strategy. So what we are doing now using sim_pi is to have here, we have this, which is the derivative of the distortion with respect to b of k, and we're setting this to 0. When we solve, we have y of k divided by 2, this is the reconstruction value index k, plus the y of k plus 1 divided by 2, this is the reconstruction value k plus 1, so we have exactly the same thing. This is the decision boundary k and the reconstruction values y of k. So we calculated the decision boundaries b of k, but we still need the reconstruction values y of k. So to obtain them, we can again take the derivative of d and set it to 0. But there is one problem. This time we cannot make the assumption that the probability function is constant, yeah? Because now we would like to have a dependency on a non-uniform PDF. Yeah? We could make this assumption before because we only assumed it for the small quantization intervals. Yeah? This can be true in practice also for non-uniform PDF if we have enough quantization intervals. But to keep this dependency on the PDF for the reconstruction values y of k, we will go back to this equation here, the original formulation of d, and we will have the PDF p of x and the reconstructions values, or the code words, y of k, yeah? And we'll take the derivative of this with respect to y of k and set it to 0. So this is what we are doing here. Yeah? So from here we go to here. So we'll take the derivative with respect to y of k and set it to 0. So we have also here using sim_pi. But since the y of k is only in one interval, this sum disappears. So we can remove the sum. So this is the derivative of y of k, and y of k is only in one interval, so the sum disappears, and we have this. And when we take the derivative of this with respect to y of k, that's what we are doing here. So we end up with this equation here, which is similar to this one. Now we have a sum. So we have this minus 2x p of x dx, and we have, so there's a sum here. We can split this integral in two parts. So this is what we are doing here, and we get the final result that the y of k, there is this numerator and this denominator going from b of k minus 1 to b of k. So the decision boundaries, we have our signal x, we have the PDF of our signal, and this is what we are doing also in sim_pi. So we had this equation here. We are splitting this integral in two parts, and we end up with the y of k We are solving this equation for y of k. So this is what we are doing using SymPy, and we have exactly the same result. Yeah? Now we got a result without making any assumptions of the probability function. Yeah? This can be interpreted as a conditional expectation of our signal value over the quantization interval. Yeah, or also it's the centroid. It's centroid as a reconstruction value or cold world. Yeah? The value in the numerator can be seen as the expectation value of our signal in this interval, and the denominator can be seen as the probability of that signal being in that interval. So we have this equation with the numerator and denominator, and we can observe these two things here. Yeah? It can be interpreted as given the signal is inside the interval, this is the average or expected value. Yeah? So the decision boundaries depend on the reconstruction values y of k, and y of k depends on the b of k, so we need to come up with a way to compute them, and what we do is to have an iterative algorithm. We concluded that the decision boundaries b of k depend on the reconstruction values y of k, and the y of k in turn depends on the b of k, so we will use an iteration or an iterative algorithm to solve, to compute b of k and y of k. So this algorithm goes like this. So we decide on m, so the number of quantization intervals. We will start with random assignment of m number of reconstruction values y of k. Then, using the reconstruction values y of k, we will compute the boundary values b of k as midpoints between two reconstruction values, or code words. So this is the nearest neighbor rule. Then we will use the PDF for our signal and the boundary values b of k to compute new reconstruction values, or code words, or centroids, or conditional expectation over the quantization areas between b of k and b of k minus 1. And then we will go back to step number 2, and we will keep it updating until it's sufficiently small. Yeah? So this algorithm usually converges, so it finds an equilibrium and doesn't change anymore, and it results in the minimum distortion D. Let's go through an example to see this algorithm in action. So there will be an example for the Lloyd-Max iteration. So we will assume that we have a signal that it's between 0 and 1, that it's uniformly distributed, so our p of x is equal to 1 on this interval, and we want to have two reconstruction values, or two code words y of k. So we will have three boundaries b of k. So we have the b0 is equal to 0, b2 is equal to 1, and we need to find b1. So this is a very simple example, so we can just get the feeling of how this algorithm works. So step 1, we will start with a random initialization of y1 and y2. So we choose some values for y1 and y2. Then we will apply the nearest neighbor rule. So we will calculate b1 given y1 and y2, which were random initialized. So then we have b1, so we have this value here. Then we will compute the conditional expectation. So we have this equation here for y of k. So now we have b1, and then we will use our PDF, which is equals to 1. So what we will do, we have from 0 to 0.55, so b0 to b1, and we have this part here. Then we also have the denominator here, so we're just replacing here, and then we will come up with the new values of y1 and y2 that is given by these values here, and then we go back and we will calculate again the nearest neighbor with these updated values. So now the b1 is equal to this, and then we go back to step 3 and we will calculate the conditional expectation again, and we will keep doing this until it doesn't change much more, and we will see that this should converge to y1 is equal to 0.25 and y2 0.75 and b1 to 0.5. So let's define here our functions for this algorithm. So here is a function to compute a b of k, which is the nearest neighbor rule. So we're dividing given y will be an array with two numbers, so we will take the average, and then we're also defining a function to calculate the y of k, which is given by this formula here. So this is what we're doing here. So we are using here this numerical integration from SciPy, in a previous notebook we've seen this revision on PDFs, histograms, and numeric integration. So we are using this here, and we are computing for y1 and y2, and here is where the iteration happens. So we random initialize our y, so there's y1 and y2 exactly like we did here, 0.3 and 0.8. We will define a certain number to iterate, so we go from 100 iterations, and we are defining an epsilon, so this is the small change. So if the values will change less than this, we will stop the algorithm. So we're setting that b starts equal to 0, and we have this for loop. This is the iteration. So what we're doing is we are going from this step, this step, this step, and then we keep going back to 2 and updating, and when we have a small change that we think, okay, it's good enough, we can stop. So when we run this, we see that after 14 iterations, we have that y1 is equals to 0.25, so it converges to this value as we said before. Y2 converges to 0.75, and b converges to 0.5. So this is a very rudimentary implementation of this algorithm to give it some sense of how it's working. Let's take a look at another example. This time is not a uniform distribution. We will see what happens when we have a Laplacian distribution. So we have the formula for a Laplacian PDF. So this probability function is given by this equation here. So it's an exponential at the power of minus 0.5 times modulo absolute value of x. So we will do the same thing. We will random initialize values of y1 and y2. So it will be 0.3 and 0.8, and we will calculate the nearest neighbor rule. So we have the b1 is like the average between these two values, and we have this. But now our condition expectation, we have to take into consideration the PDF of the Laplacian distribution. So before it was 1, very simple to calculate, but now we have to include this formula here inside here. And then when we compute the numerator for this, we have this part here. So when we use NumPy to compute this, we have this value of 0.126. For the denominator, so this part here, we will have this here, and we're replacing this by this function here, and when we do this, we have 0.48, and then the numerator divided by the denominator, we have this result here for y1. For y2, we need to do the same procedure, but then, so we have here the numerator and the denominator. Then we are printing the numerator divided by denominator, and we have 0.76. So this was y1, here's y2, and then we go back to step 2 until convergence. So as we did before, here is our functions to implement this algorithm. Here is the nearest neighbor rule, and here now we have this function here, but we are replacing this PDF equals to the Laplacian, the PDF of a Laplacian distribution with those values here. So this is what we are doing here. Then the same thing, we're setting this epsilon, which is our the change, when it stops to change our value according to this epsilon, we say okay, it's good enough. So we have now the iteration loop, and we have that after 28 iterations there are no significant change, so the changes are smaller than the epsilon, and we have that y1 converges to 0.23 and y2 converges to 0.72, and the b is equal to 0.47. So we've seen in action how this algorithm works for just a simple example where we had three boundaries. So we had b0, b1, and b2 for uniform distribution, for a Laplace distribution, and that's it for the Lloyd-Max Quantizer.